Hello everyone. Welcome to this lecture in the Build Large Language Models from Scratch series. This is a very special lecture because it covers one of the most fundamental aspects for building a large language model, and that is building the data processing pipeline. When people learn about large language models, I think that they do not pay too much attention to data processing, but it's really one of the fundamental building blocks of having a strongly performing large language model. So, what does it mean data processing? The main idea behind data processing is that we all know that large language models have sentences, right? And they deal with text, they deal with sentences. But if you have a big PDF file, that cannot directly be given as input to the large language model. It needs to be processed further. And that this whole procedure of processing the data before it is fed as input to the large language model is called as data pre-processing. So in our case, the data is text, the data is paragraphs, the data is documents. What can we do to this data so that it can serve as an input to the large language model? And we'll be answering this question in today's lecture. We'll answer this question in four steps, which are the four fundamental steps needed before any sentence is transformed into a form which is good enough to be an input for a large language model. The first of these four steps is called as tokenization. The second of these four steps is token embeddings. The third is called positional embeddings. And the fourth is when we create input embeddings. This is the final step, and these input embeddings then serve as inputs to the large language model. Remember that input embeddings are the summation of token embeddings and positional embeddings. So we'll learn about token embeddings in part 2, and we'll learn about positional embeddings in part 3, and then we'll sum these two to create input embeddings. Even when we look at tokenization, it can be broken down into three parts: word based tokenizer, subword based tokenizer, and character based tokenizer. The subword based tokenizer has many types, and byte pair encoder is one of them. GPT-2 and in fact many GPT models use this byte pair encoder tokenizer, which is a subword based tokenizer. Token embeddings is essentially converting token IDs into vectors. Positional embeddings is encoding information about the position. Awesome, right? So let's get started with these four steps, which we will cover in detail in today's lecture. First, we'll start with tokenization. So let me zoom in over here. So when you want to build a large language model, you need to go through three stages. Stage 1 is for building the basics of an LLM. Stage 2 is for pre-training, and stage 3 is for fine-tuning. Today's lecture comes under stage 1, and more specifically, it comes under the data preparation and sampling part of stage 1. So, as I mentioned, first we'll be looking at tokenization, and initially we'll be looking only at word based tokenizer. So, what we'll do right now is that we'll construct our own word based tokenizer from scratch. Although this is not the tokenizer which is used in GPT models, GPT use subword based tokenizer. But if we directly move to subword based tokenizer, you'll lose the intuition, you'll lose the feel of how exactly tokenization is done. So first we'll start with word based tokenizer. And for that, we'll need a database, right? We'll need a data set. Very simply speaking, word based tokenization is just converting the entire data set into chunks of words. That's it, and I'm going to show you how that is done. It's not as easy as it looks. So the data set which we are going to use is a book which is called The Verdict. It's a book which is written in 1908. You can also search about it. It has this cover, and we are going to use this as our input data set. It has a lot of text, as you can see over here. So in word-based tokenization, what our aim would be to take this text and to convert it into words and break it down into words, right? So then let's move to Python right now immediately, and let's see how to code this out from scratch. So this is the Python notebook which we'll be going through in today's lecture. The first step, as I mentioned, is creating word based tokens from scratch. So initially what we'll be doing is that we'll open this data set, we'll open this document and we'll read this document. The way it is done is that you have to use this with open, and then you assign a variable called raw text which contains the entire text which is read by Python. I've actually downloaded this book from this particular link. You can download it online. I'll share the file with you so that you can also run this code on your own. So once the data set or the book itself is downloaded or read by Python, what you can do is that you can check whether it has indeed been read. So you can print the total number of characters and you can even print some portion of the text. So you can see that the total number of characters is 20479, and here I'm printing the first 100 characters of this file. So it's I had always thought Jack Gisborne rather a cheap genius, though a good fellow. Let's check whether this is actually correct. So in the book, it's exactly the same. I had always thought Jack Gisborne rather a cheap genius. Great. So we have read the data set successfully. Now let's move next to the portion of how do we split this data into tokens. I've added a small note here, which you'll also see when I share the notebook. But when actual large language models are constructed, the data set which they process is millions of articles and hundreds of thousands of books. But for educational purposes, it's sufficient to work with smaller text samples like a single book, as I'm showing right now, because the hardware capacity, uh, it requires minimum hardware capacity and it's also much easier to demonstrate. But whatever we are seeing right now can easily be scaled up to larger and larger data sets. Now, the question which we want to ask is how can we best split this text to obtain a list of tokens? So let's see. For that, we are going to use the regular expression library in Python. So you can head over to this link, which I'll also share in the YouTube video description. And let me show you how this library can be used. So you first take some random text. I've chosen a sample text here. Hello world, this is a test. And then what we do is that we take this text, and using the regular expression library, we split this text based on wherever white space characters are there. So what this command here does is that it reads the text and then it splits the text wherever it encounters white spaces. So it scans the text from left. So first we scan it from left, and after hello and comma is encountered, there is a white space here. See? So then it splits here. Then it goes on scanning further. Then after world dot, there is a white space here. There is a white space here, here, and here. So it creates splits at those locations where white spaces are there, and you can see this is the result. So the result when we split this is hello, then white space, then world dot, then white space, then this comma, then white space, then is, then white space, then white space, and then test. Uh, do you see the problem with this tokenization? Why can't we stop over here? The reason we can't stop over here is that hello and comma are both in a single token. I don't want that. I want punctuations to be in a separate token because I want my LLM to know which are punctuations, which are normal words. So I want comma to be a separate token. I want full stop to be a separate token. Similarly, if you actually go through the text, there are so many other characters, like there is this character here. I'm sure there is a question mark somewhere. I want all of these special characters to be separate tokens split from the text. That's the first mistake here. The second mistake is that I don't want white space characters as separate tokens. Now, this is a debatable topic because sometimes it's good to have white space characters. For example, if you're writing Python code, indentations are important, right? White space characters are important. In that case, it's good to have white space characters as separate tokens. But for the sake of demonstration, I don't want white space characters. So there are two things I will modify here. I Along with splitting, here we only split where white spaces are there, right? I also want to split wherever different characters are encountered, like quotation, exclamation mark, question mark, etc. And then I want to remove the white spaces. We'll do exactly this right now. So what I'll be doing right now is that I'll take this text. Then what I'll be doing is that I'll split, but I'll split on all of these characters. So earlier we only split on the white space character, right? But now I'm saying here that whenever you encounter a comma or a full stop or a colon or a semicolon or a question mark or an underscore or an exclamation, inverted comma, bracket, slash, you split there. That's what I'm instructing this regular expression library to do. So this is the first thing I'll be doing. The second thing I'll be doing is removing the white spaces. So what this line of code does is that it scans through the result. So it scans through the tokens and it results a true value. It outputs a true value only if white space is not there. So wherever white spaces are there, it outputs a false value. So this item.strip is true only when white space is not there. Item.strip is false when a white space is encountered. So when this list of tokens is passed through this item.strip function over here, only those tokens which are not a white space will be returned. So let's print out the result and let's see the result. So here you can see hello is a separate token, comma is a separate token, world is a separate token, dot is a separate token. Awesome, right? So yeah, so hello is a separate token, comma world dot is this dash dash is also a separate token. Awesome. So now all of these separate characters are individual tokens. And we have also removed the white spaces. See, white spaces are not different tokens over here. So we have essentially taken a small sentence and we have converted it into individual tokens. Now we'll apply these same two commands on this entire data set which we are reading. So exactly the same commands will be used. We'll define a variable called preprocessed, which is a list which contains all the tokens of the entire essay. So what we are first saying is that you scan through this essay and split wherever these special characters are encountered and also split where a white space is encountered. In the second sentence, we are saying that you have take the list which is called as preprocessed right now, retain all the tokens in this list but get rid of all the white space characters. We don't need those as tokens. That's what we are saying in this second sentence right now. Great. So pre-processed is the list which contains the tokens which the essay has been broken down into. Awesome. Just to make sure we have done the tokenization correctly, what I'm going to do is I'm going to print the first 30 tokens in this list. So here you can see the first 30 tokens are I, had, always, thought, Jack, Gisborne, rather. So here you can see I, had, always, thought, Jack, Gisborne. It has been broken down into individual words, but even these characters are separate tokens. So if you see over here, this dash dash is a separate token. So tokenization is actually pretty simple. Here we are looking at word-based tokenization, where every token is a separate word or a character. And when I say character, I mean special symbols like comma, exclamation mark, full stop, quotation, etc. Awesome. So here you can also print the length of this list, which gives you an idea of how many tokens are there. So when you print it out, you'll see that we have 4690 tokens over here. And there may be duplications also because we have not gotten rid of duplicates here. That's fine. I'm just printing out the total length of tokens. It's 4690. Great. So now we have the entire data set, which is an essay. We have converted it into a list of tokens. But we need numerical representations, right? Computers don't understand words. So then we need to convert these tokens into token IDs. That's the next step. All the tokens which we have generated need to be converted into token IDs. And there is a specific way to do this. First, what you do is you take all the tokens, you remove the duplicates, and you arrange the tokens in an ascending or an alphabetical order. So let's say if the data set was the quick brown fox jumps over the lazy dog, you break it down into tokens. Let's say the quick brown fox, and you arrange them all in alphabetical order. So brown, dog, fox, jumps, lazy over quick the. And then to each of the tokens, you assign a token ID. Since they are in alphabetical order, the first token will have token ID 0, the second token will have token ID 1, etc. dot up till the end. The last unique token will have the token ID 7 in this case. So basically, this is called as a vocabulary. The vocabulary is essentially a dictionary where every unique token is mapped to a unique integer which is called as the token ID. For all practical purposes, the computer only cares, or the LLM rather, only cares about the token IDs, not the tokens, because the token IDs are have a numerical representation. So what I showed you here is called constructing the vocabulary, and the vocabulary is a dictionary which maps the tokens to token IDs. This is exactly what we'll be doing in code as well. So we have the pre-processed, right, which is a list of all the tokens. First, we need to convert this into a set. So we get rid of all the duplicates also, and then we sort it in ascending order. So you take all the tokens and you sort them in ascending order, and you can also print out the vocabulary size. So here you will see that is 1130. Now, after you sort all the tokens in ascending order, you have to assign a token ID, which is an integer to each token. So you can do that through enumerate. So when you use the enumerate function in Python, what it does is that it creates integers and tokens. So then you create a dictionary which is called as a vocabulary, and for each token in the dictionary, there is essentially an integer associated with it. And enumerate anyway lists down all the integers in alpha in ascending order. So the first token will be assigned a token ID of 0, the second token will be assigned a token ID of 1, etc. So what we can do over here is we can actually print out the items in the vocabulary, and then see the first 50 items. So here you can see first all these special characters are there who have the token ID 0, 1, 2, etc. And then all the separate tokens are associated with a token ID. So we can see that for has a token ID of 35, has a token ID of 47, etc. So it's the vocabulary is essentially a dictionary. So if someone gives you a token ID, you can see what the corresponding token is. If someone gives you a token, you can see what the corresponding token ID is. Awesome, right? So that's the second step. We have converted the tokens into token IDs. The third step, what we have to do is that we have to implement a tokenizer class in Python. What this tokenizer class will do is that it will take the vocabulary, and it will have an encode method and it will have a decode method. What the encode method will do is that for any given word, it will convert the word into a token ID. What the decode method will do is that for any given token ID, it will convert it back into the token. So let me illustrate this for you over here. So after we saw the concept of token IDs, we now need to implement a tokenizer class in Python. So whenever an instance of the tokenizer class is created, we have two methods. We have the encode method, which is tokenizer.encode. What this method will do is pretty simple. It will just take the text, break it down into tokens, and assign a token ID to each token. The second method is the decode method. What this method will do is the exact reverse. It will essentially take token IDs, convert them into tokenized text, and then generate the original sample text from these token IDs. So that's what we are going to implement now. So you can see that this is the tokenizer class. And whenever an instance of the class is created, we need to first pass in the vocabulary, which you already saw. And then we maintain two dictionaries. One is the dictionary string to int, which is of course the vocabulary, because the vocabulary is just the dictionary which converts the string to an integer. And then we have to maintain a reverse dictionary, which is integer to string. So what this says is that for every string integer pair in the vocabulary, this dictionary will be the reverse. So this dictionary will be integer mapping to string. So whenever an integer is given as the lookup, this dictionary will return this a given string. So that's the decode part. So then we define two methods. The first is encode. The encode will have exactly the same things what we saw here. So here we saw the first command was splitting the text based on these characters. The second was to get rid of white spaces. That is how we created tokens, right? So the encode method which I'm showing you has exactly the same thing. We first have this pre-processed list, and we have the whatever text is given as an input to this encode method. We'll first split it based on these characters. We'll get rid of the white spaces. Then whatever remains, for all the strings which remain, we'll see the corresponding integer in the vocabulary, and then this method will return a list of token IDs. That's it. The decode method will do exactly the reverse. It will take as input a list of token IDs, and then what it will do is that it will use this integer to string dictionary, and based on the token IDs, it will convert these integers into strings, and then it will join the different strings together. There is one more subtlety here, that when we join strings like this, there is usually a space before punctuations, and we need to get rid of that space. So that's just the second sentence over here. So this is the decode method which returns the text. Great. So this is how a tokenizer class is created. And once we create a tokenizer class, we can actually define an instance of this class. So I'm creating an instance of this class called tokenizer, and I pass in the vocabulary which I already had defined. So if you remember, this is my vocabulary based on the data, based on this data set. So now what I'm doing is I'm creating an instance of this simple tokenizer version 1 class and passing in the vocabulary. And now once an instance is created, I can access two methods, encode and decode. But for the encode method, I need some text, right? So let's give it some text. So it's the last he painted, Mrs. Gisborne said with pardonable pride. Let's see where this text appears. So pardonable. Yeah. So I'm giving this text. It's the last he painted, Mrs. Gisborne said with pardonable pride. So this is the text which I'm giving as an input to the tokenizer class, and let's see if it can encode it. So then I use the encode method for this text. When this text is passed, what will happen is that first it will split. First it will split based on the characters, remove the white spaces, and convert the tokens into token IDs. And when you print the IDs, you will see that these are the token IDs for each of these tokens. So basically, its will have one token ID, the will have one token ID, last will have one token ID, and these token IDs are printed over here. Now we can also test the decode method. So you can pass in these IDs back to the decode method, and you'll see we recover the same sentence. It's the last he painted, Mrs. Gisborne said with pardonable pride. Awesome, right? So we have successfully implemented an encoder method and a decoder method, and we have also created the tokenizer class in Python. So you must be thinking, this is great. What are the disadvantages here? Why doesn't GPT models use this kind of a word-based tokenizer? Well, there is a major disadvantage. If you come across a text, let's say the text is "Hello, do you like tea?" and if you try to encode this text with a tokenizer, you will get an error. Can you try to think why you have got an error here? You can pause this video for some time to think about it. The reason you have got an error here is that these some of these words were not present in the vocabulary. So the word hello was not present in the wordic short story at all. Hence, it's not contained in the vocabulary. So if you control F hello here, you will not see it over here. So this is the main problem with word-based tokenizer. It does not know how to deal with out of vocabulary words. So if you give it some text to encode which is not present in the vocabulary, it returns an error because hello is not present in the vocabulary. So how do I encode it? That's one of the major problems with word-based encoding scheme, and that's why we have to add special context tokens. So until now we have implemented a simple tokenizer, right? But how to deal with tokens which are not known? A simple way to do this is to augment the existing vocabulary with two tokens. The first token will be an unknown token. So if a word comes in the input text which we do not know, it will be mapped to this unknown and then the corresponding token ID. The second token, which is very important, is called end of text. So you can see here I've added these two tokens at the end of the vocabulary. So unknown token is simple to understand, but you must be thinking, what is this end of text? And this end of text token is actually also used for training GPT. When you work with different documents, which are inputs, you need to specify where one document ends and when other document starts. So when you give inputs, this is how it's done. So let's say this is the text source 1, then this is the text source 2, text source 3, and text source 4. Let's say this is a news article, these are news article, these are Reddit posts, these are blogs, and let's say these are newspaper clippings. So after this first text source is finished, we need to give end of text at the beginning of the second text source, which says that text source 1 is done. Now the text source 2 begins. Similarly, at the beginning of the text source 3, we have to give this end of text token. And at the beginning of text source 4 also, we have to give this end of text token. So when working with multiple text sources, we add end of text tokens between these texts. These tokens essentially act as markers, signaling the start or end of a particular segment. This leads to more effective processing and understanding by the large language model. And remember, when ChatGPT pre-processes the input resources, the text resources, we also give the end of text tokens. So now we are going to deal with these are called special context tokens. So we will modify the tokenizer to use an unknown token if it encounters a word that is not part of the vocabulary. And we will also add a token between unrelated text called the end of text token. So here's the all tokens, which are basically all the tokens in our current vocabulary. And we are extending this by adding two tokens at the end of this, the end of text token and the unknown token. and then we create the vocabulary again. It is the same token to token ID or token to integer mapping, but now it has two additional tokens and token IDs. That's why the length is 1132. If you look at the length of the initial vocabulary, that was 1130, right? So the length has been increased by 2, and we can even print the vocabulary and look at the last two items in this vocabulary. We have the end of text token mapped to a token ID of 1130. We have an unknown token mapped to a token ID of 1131. Great. So now we have augmented the vocabulary with these two additional tokens, and now we are ready to actually modify our tokenizer class. So our simple tokenizer version 1 class had an encode and decode method, which we are going to retain, but we are going to change some things. In the encode method, what we are going to say is that if the item does not, so if whatever is contained in text, it does not exist in this str2 int dictionary, what we can say is that you can replace that text with unknown, and then you can map this unknown to the corresponding id which is there in unknown. So unknown token is there in our vocabulary. So if some item is encountered in the string to integer conversion which is not there in the vocabulary, we replace that item or that word with unknown, and then we return the integer or the token id associated with the unknown token. That's how we'll deal with unknown tokens. The decode method actually exactly remains the same. So now let us test this simple tokenizer version 2. So I create an instance of the simple tokenizer version 2, and the text one is hello, do you like tea? The text 2 is in the sunlight terraces of the palace. So now we are also going to merge these two texts, which is the input which I'm going to test the tokenizer on. But when we merge, we are also going to give this end of text token. This is how it's done in GPT. So we could have directly given these two sentences, but we indicate when the first sentence end and when the second sentence starts. So this is my input text which I will now feed to my encode method, and you will see now there is no error. Although hello was not included in the vocabulary, what is done now is that in this simple tokenizer version 2, hello is not there in the vocabulary. So when hello is encountered by this encode method, it replaces it with the unknown token and assigns it that corresponding token ID, which is 1130. See, so that actually it's 1131 for unknown. And whenever the end of text is there, so end of text is here, we have a token ID of 1130. Great. And now you can decode it back. So when you decode it back, the decoded output will be unknown, do you like tea, end of text, in the sunlight terraces of the unknown. So there are actually two unknown words here, hello and palace, because palace is also not in the data set. But now by augmenting the vocabulary with these additional tokens, we are able to encode and decode even unknown words successfully. Awesome. So far we have discussed tokenization, and we have also seen some special tokens, and we saw the tokens like unknown and end of text. One thing to remember is that depending on the LLM, some researchers also consider additional tokens like beginning of sequence, end of sequence, then a padding token, etc. We'll not go into details about these tokens, but it's important to remember that this unknown and end of text are not the only special context tokens. There are also other tokens which some researchers consider. Now, for GPT, the tokenizer used for GPT models doesn't use an unknown token, but it does use an end of text token. Okay. Okay, so until now we have looked at word-based uh, tokenization. You can take a pause here, take a break if you want, because now we'll be moving to the next section, which is types of tokenizers, and we'll also look at the tokenizer which is used by GPT, and that's called as byte pair encoding. So GPT models use a byte pair encoding tokenizer, and we'll now learn about that. So if you want to take a break at this point, feel free to pause and then come back to this second part. Okay, so until now we looked at word-based tokenization, and we actually constructed our own word-based tokenizer. And we saw that by adding special context tokens, it could also deal with unknown words which were not present in the vocabulary. So then your question would be, why not this? Why this was not used for training GPT, and why do we even need to study about other tokenization algorithms? So, word based tokenization, as we saw, is just breaking down the sentence into individual words. The main problem with word based tokenization, as we saw, is that it gets very difficult to deal with out of vocabulary words. We need to add these special context tokens, etc. The second major problem is that, uh, let's say there are two words, boy and boys. There is ideally a lot of similarity in these words, right? But both of these words will be assigned separate token IDs, and there is no meaning which is captured in the tokenization because the token IDs are different. There is nowhere we get some kind of an intuitive meaning that these two are similar. They actually contain the same root word. So the second major problem with this is that we do not understand the similarity between words based on their root words. All of that meaning is lost. And the third major problem is that it leads to very large vocabulary sizes. Because if you are training GPT, and if you look at the number of words in the English language, let's actually see. We only looked at this data set, right? But for training GPT, you will need to have a vocabulary with a huge number of words. So, number of words in the English language. So let's see. So the number of words in the English language are estimated to be around 600,000 to 1 million. That's a huge number of words, right? So to actually make a vocabulary for this, we would need a vocabulary size of this much, which is really very high. So word-based tokenization schemes also need a very large vocabulary size, and that's a big problem. Uh, then how to solve these problems? There is another end of the spectrum, which is essentially character-based tokenization. What happens in character-based tokenization is that when you look at sentences, different words are not tokens, but instead characters are the tokens. So instead of the tokens being my hobby is playing, the tokens are now MYH. That's it. The tokens are individual characters. Can you think of the advantages and disadvantages of this? You can pause the video here if you want. Okay, so the major advantage of this approach is that it leads to a very small vocabulary. Remember, one of the major problems of word based tokenization is that we would need a large vocabulary, but the number of characters in the English language is just around 256, and every language has a fixed number of characters. So, the vocabulary which we will be using in character based tokenization is actually very small. That's one of the big advantage, and it actually solves the OOV problem, which is the out of vocabulary problem. But there are some other major issues with character level tokenization. Similar to the word based tokenization, the meaning which words carry is completely lost. So, for example, boy and boys, there is no meaning encoded. The same root word is used in these two words, boy, that also is lost. Why is it lost? Because we completely destroy the words down to their individual characters, right? We get a small vocabulary size, but in essence, we are removing the soul of words, which is their meaning, by breaking it down into characters. So the meaning associated with words is completely lost. There is another major problem, and that is that the tokenized sequence is much longer than the initial raw text. So, for example, hobby, right? If you look at hobby, in word based tokenization, hobby was a separate token. But now there will be five tokens for this: H, O, B, B, Y. So, this one word is actually converted into five tokens, and this becomes a big problem when dealing with large data sets. The the tokenized sequence is much longer than the initial raw text. So these are the problems associated with character level tokenization. So essentially the major problems with word based tokenization is that it needs a large vocabulary. The major problem with character based tokenization is that the meaning is completely lost. Can we think of best of both worlds? Can we think of something which does not need that much vocabulary but it also retains the essence of words? That's where subword based tokenization actually comes into the picture. And the byte pair encoder which GPT models are using, that is actually subword based tokenization. As you must have guessed, in subword based tokenization, not full words are tokens and neither full characters are tokens, but subwords are tokens. And there are some rules for subword based tokenization. The first rule is that we do not split frequently used words into smaller subwords. So those words stay the same, but we split the rare words into smaller, meaningful subwords. Now, what does this mean? So, for example, if you consider boy and boys, Boy may occur many times in the data set, so that will not be split. That will be retained as one word, boy. But uh, boys will actually be split into boy and s. So boys is a rare word maybe, and it is also derivative of the word boy. So it will be split into two words, boy and s. So now instead of having two separate token for boy and boys, we just have one token which is boy. So you can see that this tokenization retains the root word. So boy and boys both will have the boy token as common. Just boys will have an extra token which is s. So subword based tokenization can also have entire word as tokens, can also have characters as tokens, and it can also have subwords as tokens. But it follows these two rules. So if there is a word which occurs frequently, that is retained as a single token. But if there is a rare word, that's split into smaller meaningful subwords, which retains the root word. Uh, so the subword splitting actually helps the model learn that different words with the same root word as token, such as tokens and let's say tokenizing, are similar in meaning. So this is an important point which we did not achieve in word-based tokenization and even character-based tokenization. The subword splitting actually helps the model learn that different words with the same root word, such as tokens and tokenizing, are similar in meaning. That's very important. So this meaning is actually encoded in subword-based tokenization. Now, how is subword based tokenization implemented? There are certain algorithms to implement subword based tokenization, and one such algorithm is called as byte pair encoding. So, this algorithm itself was developed in 1994, and the main purpose of this algorithm was to compress data. I'll not spend too much time on it, but let me take you through a quick example. So, let's say if this was the original data, what happens in this algorithm is that we actually first look at a byte pair which occurs the most. So in this case, AA is that byte pair, right, which occurs the most. So we look at the byte pair which occurs the most, and we replace the byte pair with another variable which does not occur in the data. So AA appears the most. So we'll replace it with another variable which is called as Z. So now the compressed data becomes ZABD, ZABAC. Then we look for the next common byte pair, that is AB, and that is replaced by another variable which is Y. So then the further compressed data becomes ZYD, ZYAC. So only one byte pair is left, and after that we do not do the compression further. There is one more round which can be done. This ZY can be replaced with W, and this ZY can be replaced with W. So that is the last round of compression. This is how the byte pair encoding algorithm works. We look at byte pairs which occur the most, and we go on replacing them with different variables, and we compress the data. So you must be thinking, how is exactly the byte pair algorithm used for large language models? And how does it relate to the subword tokenization rules which we saw? So we saw that in subword tokenization, uh, the most commonly used words are represented as a single token, while rare words are broken down into two or more subword tokens. We'll see that this is exactly what the byte pair encoder algorithm achieves when it's applied to sentences or when it's applied to vocabulary. So essentially, let's take a practical example. If you have this data set of words, let's say if you have this is your vocabulary, let's say old appears 7 times, older appears 3 times, finest appears 9 times, lowest appears 4 times. So what you do first is that you add another token which is similar to the end of text token which we saw earlier. This token indicates that a word has ended. So after each word, you add this token. So now this is our vocabulary. Now let's see how a subword based tokenization or how byte pair encoding is actually done. First, what's done is that all the words are split into their character based tokens, into character level. So in this vocabulary, we have all of these different character level tokens, and we also mention their frequency. Next, what is done is that similar to the byte pair encoding algorithm, we look for the tokens with the most common pairing, and then we merge them. So let's look at these words. It seems that the most common pairing is E and S because it comes in finest 9 times and lowest 4 times. So it comes 13 times, right? So the most common byte which starts with E is ES. So this is actually the byte which occurs the most. So then what we'll do is that we'll merge E and S, and then we'll create a separate token. So now the new token which is created is ES. And then we'll apply the same thing. Then ES is one token. Then we look for the next commonly occurring byte. and that is EST. So then EST, in the next iteration, EST will be a separate token. In the iteration further than that, EST followed by this slash W will be a separate token. Then we'll see that the bytes O and L also appear 10 times. So then we'll merge O and L into a separate token. Then we'll see that O, L and D is that byte pair which is also occurred 10 times. So we'll merge them. So finally, the list of tokens which you will have will look something like this. This is the final list of tokens after you do 4 to 5 iterations of the most commonly occurring bytes and if you merge them. So these will be the list of tokens. Now if you analyze these list of tokens, there are also characters in these tokens, but there are also words in these tokens. And the beauty of these tokens now is that we are retaining the root words. Because if you see, let's look at our words in the vocabulary. EST occurs in finest and lowest, right? So EST is a root word which can occur in many words. And the word based tokenizer and the character based tokenizer will never learn this. But now we have learned this. Even older, if you see older and old, these would be two separate tokens in word based tokenizer. But now old is a token and then E and R are separate tokens. That's exactly how subword based tokenization actually works. We retain the root words and some kind of meaning is encoded. And since it's not exactly word based tokenization, also, we don't need that much amount of tokens to construct a vocabulary. So now in this simplified example, this list of 11 tokens will serve as our vocabulary. And then you must be thinking, when do these iterations stop? When do we stop this merging? We stop this merging of bytes based on, let's say you have a maximum token count, or let's say if you have already specified the maximum number of iterations which will happen. So this is a gist of how the byte pair encoder algorithm actually works. We have an entire separate lecture devoted to this. You can have that. You can look at that lecture. It's a 1 hour lecture which goes into a lot of detail of byte pair encoder. But here I just wanted to give you an overview of how the BPE algorithm works and why GPT is using it. GPT is using it because it also does not want a very large vocabulary size, which would have been needed in word based tokenizer. And we also need to retain some kind of root meaning. Like we know that EST is a root word. So we retain that. And we don't want a separate word for old. We don't want a separate token for older. Instead, I'll just have a common token for old. So byte pair encoding is the best of both worlds. It's an efficient vocabulary size. It also retains meaning. Awesome. So that's why actually GPT uses the byte pair encoding. What we can do right now in code is we can have a simple implementation of the byte pair encoder algorithm, and let's see how this actually works. So there is a Python library which is called as tick token, and this is the byte pair encoding tokenizer which is used in OpenAI models. So we are going to use the same tick token. So you need to first install the tick token library, and then you can actually directly create tokenizers. So what I'm doing is I've created a tokenizer from tick token, and I'm using the same encodings which are used in GPT-2. Remember our previous tokenizer class had this encode method and the decode method. Similarly, here also we have the encode and decode. So let's see we give this text which we had already given in the previous example. And you see in word based encoding we have to augment the dictionary with special words, right? But as you will see over here, this byte pair encoding tokenizer deals with this unknown text. So I've given this text here: hello, do you like tea in the sunlit terraces of some unknown place? Some unknown place is not even a word. So ideally the tokenizer should show an error, right? Let's see if it's indeed the case. So now I do tokenizer.encode text, and I allow the special character end of text. So here you see when we encode there is no error. So how do you think the BPE tokenizer dealt with this random word? Remember, the byte pair encoding tokenizer is a subword based tokenizer. So it has characters and it has subwords also as tokens. So it is very likely that this word is actually an accumulation of these characters or subwords. That's the advantage of that's another advantage of byte pair encoder tokenizer. We don't need to create special tokens like unknown tokens. With the same vocabulary of tokens which we have, it can actually replace any word which is even not present in the vocabulary. So three advantages of byte pair encoder. First, the vocabulary size is not too high. Second, it retains the meaning of root words. And third, it automatically deals with unknown words. So the vocabulary size of byte pair encoder, which was used in GPT-2, was around 50,000. You can see that it's much lesser than the total number of words in the English language, which is what we might have required if we use the word-based tokenizer. You can also Google this. So number of or the vocabulary size, uh, vocabulary size of BPE tokenizer used for GPT-2. So let's see. So the it has 50,000 tokens. Yeah. So close to around 50,000 tokens. So awesome. So this encoder method works without mentioning special unknown tokens also. And now we can also do decoder. And now you can see, hello, do you like tea in the sunlit terraces of some unknown place? Even the decoder works perfectly. So instead of writing our own word-based tokenizer, what actually works the best is using subword-based tokenizer, which employs byte pair encoding. It's already provided to us by the tick token library. We can use tick token.get encoding to create the tokenizer, and then we can test the encode and decode methods. There are some notes here. So the first note which is important is that the BPE tokenizer encodes and decodes unknown words such as some unknown place correctly. It can handle any unknown word. So how does it achieve this? That's the important question, right? So the algorithm underlying BPE breaks down words that aren't in the predefined vocabulary into smaller subword units or individual characters, as I said. And this enables it to handle out of vocabulary words. So let's say you are given this and you want to encode it, right? If you use a word based tokenizer, it will fail here because these words are not there. This is not a word. But if you encode this, it will print out some token IDs. Why this is the case? So I have a screenshot here. So let's look at this screenshot. What the BP algorithm is actually doing is that all of these, which are individual subwords or sub characters, are tokens. So whenever this new word is given to us, it's usually broken down into these tokens, which are either subwords or which are characters. So that's how it deals with out of vocabulary words like this, which don't even mean anything. And of course, then the decode method also works and it returns back the same sentence to us. So here I've done some exploratory thing, like I got the encodings for GPT-2 and I got the encodings which are commonly associated with GPT-3 and GPT-4, and I printed out the vocabulary size. So you can see that the vocabulary size subsequently increases because as better and better models of GPT are trained, we have a larger and larger and larger vocabulary. Okay, so this is how the byte pair encoding algorithm actually works. We will not cover character level encoding because that is not generally employed in large scale LLM models. So now let's go to the start of this lecture and let us see how much have we covered so far. Okay, so yeah, right over here. So until now we have covered, I think, tokenization. That's the first section which we have covered. It took some time, but it's very important. Now let us move on to the next parts, which are token embedding, positional embedding, and input embedding. So if you look at this figure, this is what we are covering. Up till now, we have finished tokenization and we have finished token IDs, and now we will cover token embeddings and positional embeddings. So if you want to take a break over here, please pause this video, take a break, and then we'll start with these sections. Okay, so I hope everyone is with me until now. It has been a long lecture so far, but I hope you are energized and excited for the next part. And here, as I mentioned, we have got the token IDs, but these token IDs need to be encoded into a higher dimensional vector space. That's called token embeddings, and then we need to add positional embeddings to these token embeddings to create input embeddings, which will be the final input to the large language model. So let's begin this embedding journey, and this journey begins with token embedding. So okay, let me scroll down to my lecture notes. Yeah. So before actually coming to token embeddings, there is one more small point which I want to cover, and that point is actually extremely important. I could have directly skipped to the embedding portion without covering this point, but I want this lecture to be as close to real life as possible. So I want to show you all the finer things which need to be considered when dealing with the data pre-processing. And one such thing is creating input target pairs. So let's see what this actually looks like. To start discussing about giving an input to the LLM, we also need to have a discussion of what the input really looks like. So we know that LLMs predict the next word, right? That's the main task which LLMs do. So if you have the first word LLM, it will predict the next word learn. If you have LLMs learn, it predicts the next word to. If you have LLMs learn to, it predicts the next word predict. If you have the LLMs learn to predict, it predicts the next word which is one. So there is an input and there is a target, but we now need to see how to represent this in numerical format. And the way this is done is as follows. First, we need to determine a variable which is called as context size. Context size is the maximum length of the input which the LLM sees at one time, which basically means how many tokens will the LLMs process to predict the next word. It can be 4 tokens, it can be 256 tokens. In large models, the number of tokens which the LLM sees is usually pretty large, more than 150, more than 200, it can even be more, around 500, etc. For now, here I am showing a context size of 4, which means that at one time the LLM can see a maximum of 4 tokens. So what we do is we create input output pairs based on this context size. So here is one sample input output pair. When the LLM receives this input, it has to predict the next word in the output. So for example, if one is an input, the next word which is predicted by the LLM should be word. If one and word are the input, the next word predicted by the LLM should be at. If one word at is the input to the LLM, the next word predicted is a. And if one word at a is the input to the LLM, the next word which is predicted is time. So this is how the input output pairs need to be constructed. So remember, when you look at one input output pair, there are actually multiple prediction tasks which are happening. So if you look at this input output pair, there are 4 prediction tasks happening, right? If one is the input, word is the output. If one word is the input, at is the output. If one word at is the input, a is the output. If one word at a is the input, time is the output. So there are 4 prediction tasks. So keep this in mind. So what we now need to do right now is that we have to, if provided a text sample, which is a text sample which is like this, we have to break this text sample down into input output pairs like these. We have to break down the text sample into input output pairs like this based on the context size. So let's see what this will look like. So our main aim is to create the input output pairs, right? And the way we will do it is by using something called as data loader. So before I started learning LLMs, I had not used data loader before, but it's actually a very useful uh, tool, I would say, which is provided through PyTorch, and it just helps to process data in a much better manner. So what we are going to do here is that we are going to create this input output target pairs through a data loader, and we'll use a sliding window approach. Don't worry about these terminologies, I'll explain what it actually means. So what we are going to do here is that, let's say this is sample text. In the heart of the city stood the old library, and let's say we are using a context size of 4. Okay, so I will create two tensors based on the sample text. One will be my input tensor and one will be my output tensor or the target tensor. Let's look at the input tensor first. Each row of the input tensor will be uh, an input to the LLM, and each row of the target tensor will be an output of the LLM, very similar to the input output pair which we just saw over here. This is an input output pair. So the first row of the tensor x and the first row of the tensor y will be an input output pair. The second row of the tensor x and the second row of the tensor y will be another input output pair, etc. So using data loader, we'll first collect. So using data loaders, we'll collect the inputs in a tensor X, where each row represents one input context, and we'll also create another tensor Y, which consists of the corresponding prediction targets. So if you look at the prediction targets, they are just the input which is shifted by one word. So remember, this is important. The prediction. So if you look at the target, If you look at the first row of the target, it's actually just the first row of the input but shifted by one word, because we are going to predict the next word. That is important. So let's see how these input output pairs are actually created using the data loader. So I'm going to scroll down right here. Yeah. So we have implemented this byte pair encoder tokenizer, right? And using this tokenizer, we encoded some sample text. But now we'll encode the entire uh, data set which we are using in this lecture. So the way to do this again is we first read this text and store it in the raw text, and then we use the tokenizer to encode this raw text. This tokenizer is this byte pair tokenizer which we have got from tick token. Okay, so we are encoding this raw text now, and if you print out the length of the encoded text, it is 5145, which are the number of tokens in the training set after applying the byte pair encoding tokenizer. So now what we'll be doing here is that here I have just mentioned what the input output pairs can look like. So if you have this x as an input pair and y as an output pair, if 290 is the input, 4920 is the output. If 290 comma 4920 is the input, 2241 is the output. So there are basically four prediction tasks happening in one input output pair, similar to what we discussed on the whiteboard. This can also be printed out in textual format. So if and is the input, established is the output. If and established is the input, himself is the output. If and established himself is the input, in is the output. This is what we want. So we want to create input output pairs such as these. So this is an input output pair. And for that, we'll use the data loader. So let's see how we'll use the data loader. So it's actually very simple. We first encode the entire text into token IDs, and then what we are going to do is we are going to chunk this book into overlapping sequences. So this is one more thing, the one more concept which I want to explain here is that before we learn about chunking, you need to understand the concept of stride. So let's say here in this case, my first input is in the heart of, right? My second input here is the city stood the. So if you actually let me scroll down below where I have the photo. Yeah. So let's look at this second example first. My first input is in the heart of. My second input is the city stood the. So let's mark these two inputs. Let's mark the first input and the second input. So here the stride is 4 because the input moves by 4 positions. So if this is the first input, to construct my second input, I have to move 1, 2, 3, and 4. Then to construct my third input, I will move to the this position. Then my third input will be old library or relic. So this is stride equal to 4. So here what I'm doing is I'm not missing out any word, but between my different inputs there is no overlap. Now in this first example, you see stride equal to 1. And why is this stride equal to 1? Because the first input here is in the heart of, and the second input is the heart of the. So see, there is an overlap between the first input and the second input because the stride is 1. If the stride is 4, it leads to this second example over here. So the stride actually determines how much we move from one input batch to the next input batch. So that is another important variable when we construct the input data. So that's why it's called as a sliding window approach. If the stride is equal to 1, we just slide by 1 to create the next input. But if the stride is equal to 4, we stride by 4 to create the next input. So that's why it's sliding window approach. So what we are doing here is that the final input tensor will be input IDs and the target tensor will be target IDs. So to visualize this, you can just think of these two tensors over here. Yeah, the input tensor will be x and the target tensor will be the target id. And what we are doing here is that we are appending. So we are first looping over all the token IDs based on the context length and the stride which we have, and then we are appending the inputs to the input chunk. So we are appending the input chunks to the input IDs tensor, and we are appending the target chunk to the target IDs tensor. And what is the input chunk? It's just the token. It's just the four token IDs at one time. That's it. And what is the target chunk? It's just the input chunk shifted by one. So let me show this to you in here. So when the code is implemented, the this first row is the input chunk. that is appended to the input tensor. This first row of the target is the target chunk that is appended in the first iteration. In the second iteration, the second row is appended, second row of the input and the second row of the target. Similarly, we loop over the entire text and we append the input tensor and we append to the target tensor. So at the end of this data loader, when this data loader is created, we have the inputs and outputs. Uh, so I hope you are understanding this part. This is a bit of a detail, but it's very, very important because what this data loader enables us to do is enables to include the stride, and later you will see that it also enables us to do batch processing, parallel processing, etc. Until now, just remember that we have created input output pairs like this. We have created input pair and we have created output pair. And now what we have, so this is the just the data set. So we created the input data set and we have created the output data set. We have to pass this data set now to the data loader. So what the data loader does is that it takes the data set, and then it also takes some other attributes, like we have to specify the batch size. This is very important. Batch size is basically how many input batches do you want to process at one time before updating the parameters. This is the exact same notion as the batch size in other machine learning frameworks. So a batch size of 1 will mean that only one input output pair is processed at one time before updating a parameter. If batch size of 4, it means 4 input output pairs are processed before updating the parameters. There are some other things here, such as number of workers. Number of workers means how many threads you want to split the code on your CPU, let's say for parallel processing. You don't need to worry about this right now. So data loader is basically something which can be used to process the data set, basically the input output tensors which we described here. What the data loader will do is that it will go over these input and output tensors, and it will generate the input output batches. So after creating the data loader, you can actually print the input batch, you can print the output batch, and this is what it looks like. So this is the first batch of input, this is the first batch of output, this is the second batch of input, and this is the second batch of output. You can also do a batch size of 8, and when you use the data loader with a batch size of 8, these are the input output tensors. So since we are doing a batch size of 8, it means the LLM parameters which we'll look at later will be updated only after this entire batch is processed. So you'll see the input has actually 8 inputs and the output has 8 rows. So each row, so this is the first input and this is the first output, this is the second input and this is the second output. What this actually means that is that there are 4 words in the input and there are 4 words which need to be predicted in the output, like the next word. So each input output pair has 4 prediction tasks which we learnt about before. Okay, so until now, what we have done is that we saw the word embedding, we saw the word tokenization, we saw the byte pair encoding, which is subword tokenization. Before coming to uh, vector embedding or positional embedding, it was very important for me to tell you how the data itself is loaded, how the inputs are given, and how the outputs are given to the LLM. And I also wanted to show you the importance of context size and stride. If you did not understand this data loader part, if you did not understand data sets and data loaders, I'll also share this link in the information section. But you can now try to proceed to the next part. We don't strictly need to understand data sets and data loaders before understanding the token embeddings, which I'm coming to right now in the next section. So again, you can take a break here and focus your full energy on what is going to happen next, which is token embeddings. Okay, so now we are ready to proceed with the next section, which is token embeddings. So up till now, we have looked at tokenization, we have looked at converting tokens to token IDs, we have looked at the byte pair encoding, we have looked at data sets and data loaders. Now let's come to the next step, which is token embeddings. Um, so before actually looking at the code for token embeddings, I also want to intuitively show you why token embeddings are needed in the first place. And why can't we just use token IDs as inputs? So we saw the data sets and data loaders, and we saw that inputs have token IDs, right? Why can't we just leave it at that stage? Why are embeddings needed? So to motivate the concept of why embeddings are needed, let's look at this. So computers need numerical information, right? It requires numerical representation of words. So how can we represent words in numbers? You might be saying that this is already done in token IDs, right? We can just assign one token ID to each word and that's it. We can maybe even assign random numbers to each word. So then every word will be a number and computer or the LLM rather would understand that information. What's the problem with that? One of the major problem with that is that, let's say if you have two words, cat and kitten, these words are semantically related. But if you randomly assign token IDs or numbers to these words, that semantic relation or that meaning between these words is not captured at all. Because let's say the token ID for cat is 34, let's say, or the number associated with kitten is minus 13. We are nowhere encoding this information, right? That cat and kitten are actually related to each other. So then you might think that what about one hot encoding? What if I create a dictionary of words and wherever that particular word appears, I'll just represent it by one, all others will be zero. So then dog, let's say, will be 0000100 dot dot dot. Puppy would be something like 0000100 dot dot dot. So the one will appear at different positions for dog and puppy. The same problem exists for even this case. One hot encoding fails to capture the semantic relationship between the words. So even if we do one hot encoding, nowhere we are saying that dog and puppy are actually related to each other. So the semantic meaning between the words is lost if we just used one hot encoding. And that's where token embedding actually comes into the picture. The main idea is, let's say if we have four words, dog, cat, apple, and banana, and let's say I represent each word in a vectorial format. And how to get this vector? Let's say each vector has five dimensions based on has a tail, is eatable, has four legs, makes sound, or is a pet. And let's say I fill in the information for the dog. So then dog will be represented, let's say, by a five dimensional vector. And you can see that has a tail, has four legs, makes sound, and is a pet have higher values. Now when you encode cat, you will see that has a tail, has high value, is eatable, has low value, has four legs, has high value, makes sound, has high value, and is a pet has high value. Now, when you look at the vectors for dog and cat, you can see that the dimensions for which dog is higher is also the same dimensions for which cat is higher. So there is some meaning which has been encoded here, right? You can look at these vectors and you can say that these vectors are actually similar to each other. So maybe if you plot these vectors in a five dimensional space, they will be grouped together. That implies that dog and cat are actually related. They are words which are similar to each other. They are both animals. They both have four legs. They both make a sound. They both are pets. They both have a tail. Similarly, if you encode apple and banana for has a tail, for has four legs, for makes sound and is a pet, they will have lower values. But apple and banana will have much higher values for is eatable. So if you look at apple and if you look at banana, you'll see that these two vectors are closer to each other. And if you look at dog and if you look at apple, you'll see that they are very far apart because apple has a high value for is eatable and dog has a low value for that. So if you actually can embed words as vectors, then you can capture or retain the semantic relationship or meaning between words. This is an extremely important idea, and that's where token embeddings actually come into the picture. If we do this, if we can successfully embed words as vectors and capture the meaning between them, and if we feed these inputs to the LLM, then those inputs will have a lot more meaning, and that will lead to much more successful LLM models rather than randomly giving token IDs. So this is the main idea behind token embedding or vector embedding. Vectors can essentially capture semantic meaning. Now you must be thinking that, okay, this is great, but how do I generate these vectors? How do I get the values for these vectors? And actually, to get the values for these vectors, we have to train a neural network and we have to create vector embeddings. So if you look at GPT and if you look at the vector embeddings, it's a huge high dimensional space. And so every word is converted into that higher dimensional space vector, and a neural network is essentially trained to generate those vectors. Now let me come back to the whiteboard again. Okay, up till now, hopefully you have understood why token embeddings are needed in the first place. And now let us start with the next section, that how token embeddings are actually created for large language models. So to understand this, we again need to start from the vocabulary. So let's say that we have a vocabulary of words, so vocabulary of tokens, and there is a token ID, right, associated with each token. So we need to convert every token ID into a vector, right? So let's look at this matrix here. So this is a matrix which is called as the embedding layer. This is called as the embedding layer weight matrix. So what is actually happening in this matrix is that if you have token IDs such as 0, 1, 2, 50257, which are the number of token IDs for training GPT-2, for each of these token IDs, you will have a vector. So let's say if the vector dimension is 256, for example, I think a vector dimension of 768 was actually used for training GPT-2, but let's consider 256 for now. So each token ID will be represented as a 256 dimension vector. So token ID 0 will be a 256 dimension vector, token ID 1 will be a 256 dimensional vector, right up till token ID of 50257, that will also be a 256 dimensional vector. So this is now a embedding layer weight matrix which has dimensions of, so it has 50257 rows and it has 256 columns. So this embedding matrix needs to be constructed, and then whenever we want to fetch an embedding vector for a particular ID, we just look at that particular row. So for example, if we want the embedding vector for ID number 2, we just look at the third row because Python has zero indexing, and then we retrieve the embedding vector for that particular ID. That's it. That's the simple idea behind the embedding layer weight matrix. So let us look at that right now. Okay. So for the sake of simplicity, right now we are going to look at a vocabulary size of 6, and we are going to look at a vector dimension of 3. So you can think of this table, but you can think of the vector dimension as 3. So there will be 3 columns, and there will be 6 rows because the vocabulary size is 6. So let's say these are the input IDs 2, 3, 5, and 1, and we want to convert these input IDs into vectors. Like each of these input ID will be converted into a vector. So first we will actually create an embedding layer, and I think I should write it down over here. So first we'll create an embedding layer like this, and this embedding layer will actually have 3 columns, and it will have 1, 2, 3. It will have 6 rows. Why will it have 6 rows? Because we have 6 token IDs. We have token ID of 0, token ID of 1, token ID of 2, token ID of 2, token ID of 3, token ID of 4, and token ID of 5. So we have 6 token IDs, and each token ID will be represented as a three-dimensional vector. So this is the embedding layer matrix. How is this created in Python? In Python, it's created by using torch.nn.embedding, and you specify the number of rows, which is the vocabulary size. You specify the number of columns. So let me show you torch.nn.embedding. So if you go to torch.nn.embedding, you will see the documentation for this. Basically, you can specify the number of embeddings and the embedding dimensions, and it creates a matrix with randomly assigned values. So after you create the embedding layer, you can print out the embedding layer weights, and you will see that we have 6 rows and 3 columns with randomly assigned values. So here's the embedding layer weight matrix, and random values will be assigned to all of these. So for the first ID, random 3 values will be assigned to create the vector. For the second ID, random values will be assigned. Similarly, for ID number 5, random values will be assigned. One very important thing to note here is that these values are random currently, right? Because we don't know the ideal token embedding. Even this has to be learned when we train large language models. So dog and puppy needs to be closer. So the vectors for dog and puppy should be aligned. We cannot have random values like these. And we also have a neural network for this which needs to be trained. So even token embeddings need to be trained, and GPT, when it was trained, even the embeddings were trained along with the next word prediction task. So these are the, if you print out the embedding layer weights, these are the all the weights. And then, as I mentioned, you can retrieve the embedding vector for any ID which you want. So if you want the embedding vector for id number 3, you just pass in that particular id, and then you will get the vector, because then it's just the fourth row. So if you want to get the embedding vector for id number 3, you just pass in this value, and then you will get the vector. So one way to think of this embedding layer matrix, it's a lookup table, and you can actually pass in the id and you will get the corresponding embedding vector. So here you can see I've passed the id number 3, and I've got the token embedding vector for that id. We can also pass all the input ids which we want the embedding or the token embedding for at one point, and then based on the embedding layer weight matrix, we get the embedding token embedding vectors for all the input ids. So essentially what we are doing in this token embedding section is that every token id is converted into a token, into a vector, into an embedding vector. And the best way to do this is to use the embedding layer in pytorch. So when you create an embedding layer, you have to specify two things. You have to specify the vocabulary size, and you have to specify the vector dimension. Why? Because you have to create a vector for every token id in the vocabulary. So the number of rows will be equal to the vocabulary size, and the number of columns will be equal to vector dimension, because for every token id we will get a vector of those many dimensions. And then it's also important to note that this embedding layer weight matrix is actually optimized during the llm training process. That's very important. So all of these parameters also need to be optimized. And the last point to note in this token embedding section is that the embedding layer, if you look at it, it's just a lookup operation basically, that retrieves rows from the embedding layer weight matrix using a token id. Now actually what we can do is that before we move to position encoding, we can use the actual value of the token vocabulary size, which is 50257, used in GPT-2, and we can use a vector dimension of 256 to construct a very real life or practical embedding layer matrix. So that's what we'll be doing in code right now. So let me go to that particular section in the code. uh, okay, so first, yeah, this is positional embedding, but first I want to create that matrix, and then we will come to positional embedding. Yeah. Okay, so now what I will do is that I will create an embedding layer matrix which has 50257 rows and which has 256 dimension vectors. So let's see how we are going to do that. So let's say the vocabulary size is 50257, and the vector dimension which we want for each token ID is 256. So we'll use the same function torch.nn.embedding. This will create an embedding matrix with a vocabulary size, which means number of rows of 50257 and number of columns of 256. Now what we'll do is that we have already created the input data from the data loader, right? We will get that input data initially, and then this input data has token ids. So we'll pass those token ids into the embedding, and then get the corresponding embedding vectors for those token ids. It's actually a very simple concept, but you just need to pay attention to dimensions here. So remember, what we are trying to do here is that we have this embedding layer weight matrix, which is essentially a lookup table, which means that if you provide a token id, it will give you the embedding vector. But to get the token ids, we need to get the input data from the data loader. And the data loader, we are going to get input data in batches of 8, and then context length is 4, which means that at one time we are going to look at 8 text samples with 4 tokens each. So if you look at the first batch of this input data, it has 4 tokens. If you look at the second, actually this all is one batch itself, I should rather say. If you look at the first row of the input data or the first input sequence, it has 4 tokens. If you look at the second row of the input data, uh, which is the second input sequence, it has 4 tokens. So we have to essentially get all of these token IDs. Each token is one token ID, and we have to convert it into vector representation. And we are going to do this in code. It's very simple. Just keep in mind the dimensions. Keep in mind this dimension of 50257 rows and 256 columns. And here keep in mind that we have a context length of 4, which means 4 columns and 8 rows. Okay, so we are creating a data loader here, which takes in the raw text, batch size of 8, and we are going to use a maximum length, which is the context size of equal to 4. And we are going to generate the inputs and the targets. So let's just look at the inputs right now. So if you see, these inputs are exactly the same as what I was showing to you in this whiteboard. So every row essentially has 4 tokens and we have 8 rows because each batch has essentially 8 input sequences. Now we want to convert each of these token IDs into 256 dimension vector. So if you see, this is currently 8 by 4, right? This is 8 by 4 dimensions. Now we want to convert all of these into a 256 dimensional vectors. So let's see how the dimensions will play out. So we have these inputs, right? So let's say this is a 8 by 4 matrix and these are the input IDs. So we have to essentially take each input ID here, go to the lookup table and get the corresponding vector for that input ID, right? That is what we are going to do. So one embedding vector of length 256 is generated for each token in this input matrix. So if you actually see how this looks like, it's like this. So if you look at the first token ID, this will be a 256 dimension vector. If you look at the second token ID, this will be a 256 dimension vector. If you look at the third token ID, it will be a 256 dimension vector. So now every single token ID here is a 256 dimension vector. So you can think of this result as 8 by 4 by 256. So here there are 8 by 4 entries, right? And each of these 8 by 4 entries has now a 256 dimension vector associated with it. So the result of this embedding is that when we generate this embedding vector for each of these inputs, we'll have an 8 by 4 by 256 tensor. So that's exactly what is happening right here. So we have the token embedding layer and we are passing these inputs, which are the input IDs basically, and the result will be the token embeddings, which is the result, will be an 8 by 4 by 256 vector. So this is how the token embeddings are obtained in practice for a batch size of 8, for a context size of 4, and for a vector dimension size of 256. Now we will add the positional embeddings on top of these token embeddings for one batch, and then that will be the input to the large language model. So now we are going to come to positional embedding or positional encoding. It's used interchangeably. Again, you can pause here for some time, um, because positional encoding is actually going to be the last section of this long lecture. So you need to be energetic and motivated in this last part also. So I'll just meanwhile scroll to the positional embedding section on the whiteboard. Yeah. Okay, so thanks a lot everyone who have stayed until this part, which is the last part of this lecture, and that's on positional encoding. So up till now we have looked at token embedding, and we also saw how to convert all the input token IDs into token embedding vectors. The problem with token embedding is that it does not take into account the position at all. So basically, if there are two sentences, the cat sat on the mat, and the second sentence is on the mat, the cat sat. So cat, the word cat comes in both sentences, right? But the embedding vector for both these words will be exactly the same. It does not contain any information about the position. So the cat word comes in different positions in these two sentences. And ideally, where the position is really matters for understanding the context of a sentence. So it will be very advantageous for us if, along with encoding the semantic meaning, which we did in token embeddings, if we also encode information about the position of the word in the sentence. So that's where positional encoding actually comes into the picture. The main objective here is that, or the main drawback of just token embeddings is that it does not include positional information, and it is very helpful to inject additional positional information to the large language models. There are two types of positional embeddings or encodings. First is the absolute positional encoding, and second is the relative positional encoding. What happens in an absolute positional encoding is that for each position in the input sequence, a unique embedding vector is added to the token embedding. So this figure actually explains it the best. So let's say we have tokens such as cat, The second token is, let's say, sat. The third token is on, and the fourth token is the. Let's say these are the four tokens, and for the sake of simplicity, let's say the token embedding vector for all of these four are similar. So let's say 111, etc. Now, what happens in absolute positional embedding is that another embedding vector is added to the token embedding, and that is the positional embedding vector. And since these words have different positions, so cat is first word, sat is second word, on is third word or third token, and the is the fourth token, they will have different positional embeddings. So for example, the positional embedding for cat will be 1.1, 1.2, 1.3. The positional embedding for sat will be 2.1, 2.2, 2.3. The positional embedding for on will be 3.1, 3.2, 3.3. The positional embedding for the will be 4.1, 4.2, and 4.3. And then you add the token embedding to the positional embedding, and then finally you get input embeddings. And then this will be 2.1, 2.2, 2.3 for the word cat. This will be 3.1, 3.2, 3.3 for the word sat. It will be 4.1, 4.2, 4.3 for on, and it will be 5.1, 5.2, 5.3 for the word the. So these are the input embeddings which will then be finally used by the LLM. And if you see, although the token embeddings are similar, the input embeddings are different from each other because now the position is encoded. So the input embeddings for cat sat on the mat will be different than the mat the cat sat on, let's say. So here the position is taken into account. So the positional vectors have the same dimension as the original token embeddings because you have to add the positional embedding vectors to the token embeddings. Relative positioning or relative positional encoding is a bit different. The emphasis here is on the relative position or the distance between tokens. So rather than focusing on at what exact position the token is, the model instead focuses on how far apart the different tokens are. So the distance between the token become very important here. So, what are the advantages, disadvantages of both these types? The absolute positional encoding is very much suited when fixed order of tokens is crucial, such as sequence generation. So, GPT uses absolute positional encoding, and it is more commonly used than relative positional encoding. Even today, we are going to learn about absolute positional encoding, but even relative positional encoding is actually suitable for tasks like language modeling or long sequences where the same phrase can appear in different parts of the sequence. So for that, relative positional encoding can also be used. But today we are going to learn about absolute positional encoding. Okay, so we have until now we have got this token embeddings, right? So we have a tensor of 8 by 4 by 256. The next step is that we need to create another embedding layer for positional encoding or for positional embedding. So remember, one thing which is very important here is that uh, every input essentially just has four tokens, right? So the context length is important when we create the embedding layer matrix for positional encoding. The vector dimension, of course, can be 256, which is the same dimension as the token embedding, and that needs to be the same because we are going to add the positional encoding vector to the token encoding vector. But we actually need these vectors for just four positions because the context length is 4. The token id can be either in position number 1, position number 2, position number 3, and position number 4. And for each of these positions we need a separate vector, which is the positional embedding vector. So the size of this positional embedding matrix will just be 4 rows and 256 columns, because for each position 1, 2, position 1, 2, 3, and 4, we need a separate vector which is 256 dimensions. So that is what we are going to do right now. So yeah, when the input batch comes like this, if we look at first input, it will be something like this. It will have four token IDs and each will be 256 dimensions. So if our positional encoding has four vectors and each is 256 dimension, then we'll just add it to each input in the batch. So that is what we'll be doing. So we need only four positional embedding vectors, and now what we'll be doing is that we'll generate the positional embedding matrix and then create the four positional encoding vectors from it. As you can see, I sometimes use embedding and encoding interchangeably, and that's fine. So we are creating the positional embedding layer which has context length, which has 4 rows because we only need 4 vectors, and it has 256 columns because each vector will have size 256. And then what we do is that we create the 4 positional embeddings from this matrix. That's it. So then the positional embedding layer will be 4 by 256. Why? Because we have one 256 dimensional vector for each position. And now after we create the positional embedding vector, so we create these 4 vectors. As the last step, what we have to do is that we have to just add the token embeddings to the positional embeddings. So the token embeddings, as we saw, is 8 by 4 by 256 tensor, and the positional embedding is 4 by 256. So you must be thinking how to actually add these. So when you add these two in Python, it will do the broadcasting operation, which means what it will do is that it will convert these 4 by 256 into an 8 by 4 by 256 by duplicating these value 8 times. So what will essentially happen when you do this summation is that you first look at the first input sequence and you add this positional embedding for that input sequence. That will give you the first row of the input embeddings. Then you look at the second row. Even for the second row, you look at the token embedding second row. You again add these same 4 positional vectors. That will give you the second row of the input embeddings. Similarly, you look at the eighth row, which is the final row of the token embedding matrix, and again you add the same 4 positional embeddings. So then you get the final row, which is the eighth row of the input embedding matrix. And that is how the input embedding matrix is actually constructed. So this is the last step which we will also be doing in code. So input embeddings is token embeddings plus positional embeddings, and then we get the final input embedding. One thing to mention here is that similar to token embedding, even when you initialize the positional embedding, so when you initialize this positional embedding matrix, which I think I showed over here. Yeah, if you initialize this positional encoding matrix, all the values will be initialized randomly. As I said, the embedding layer in Python just initializes the value randomly. Uh, Similar to the token embedding, even the values in the positional embedding layer need to be optimized during the training process itself. So actually multiple things are happening to train the large language models. Of course, we have to train it later to predict the next word. But even in the data processing pipeline, we have to train the positional embedding. We have to train the token embedding as well, which are then fed as input to the LLM for the LLM training procedure. Okay, so this actually brings us to the end of today's lecture. This is where we started the lecture with. We started with the LLM data pre-processing pipeline, and we discussed that we'll cover all the 4 points in today's lecture. We started with tokenization. We understood word-based, subword-based, character-based tokenizer. Then we actually learned about the byte pair encoding tokenizer, which is used by GPT. And then we learned about token embeddings, which is essentially converting token IDs to vectors. We saw that it's not enough to just learn about token embeddings. You also need to essentially learn about positional embeddings as well, because these positional embedding vectors encode information about the position. And then finally, you add the token embeddings with the positional embeddings to create the input embedding. If you were to ask me for one figure to explain today's lecture, I would say in today's lecture, we have covered the entire data pre-processing pipeline shown here. So right from tokenization to token IDs to token embeddings to positional embeddings and finally to input embeddings. We covered all of this in today's lecture. This makes the data ready to be fed as an input to the LLM architecture or to the LLM pre-training process. Um, we also have separate lectures on all of these topics, but I thought to make one condensed lecture to show you all the things in one glance. As always, I take an approach of the whiteboard plus coding in Google Colab so that your theoretical foundations are strong, plus your coding foundations are also strong. I'll be sharing this entire code file with you so that you can play around with it, you can run it on your own browser, etc. Please ask any questions which you might be having in the YouTube comments, and I'll be happy to answer all of them.